All right, so we're going to talk about properties of graphs of polynomial functions. So in this first example, we're supposed to determine the types of polynomial function that f, g, and h are, graph below, and we're supposed to give a reason um, and based on the zeros of each function. So let's take a look at this first graph and identify the zeros. So you can see that I color-coded the black 0 and the purple 0. And simply put, we know that x equals 0, that has a multiplicity of 1 because the graph crosses the x-axis without changing concavity. In the purple, x is 3, and it has a multiplicity of 2 because the graph is tangent to the x-axis at x equals 3. And here's the part that you care about. So since the sum of the multiplicities of the zeros is 3, then f of x is a cubic function. So this is just an example of how you are supposed to determine the type of polynomial function. We gave a reason based on the zeros of the function. Okay, so let's go ahead and try the second one here. So if we take a look, we've got in black, I've got the zeros, x equals -3 and 3, and they have a multiplicity of 1, again, because the graph crosses the x-axis without changing concavity. And then we've got our purple. And so you can see that there is a multiplicity of 2. Am I here? Yeah, so we're here. It's tangent to the x-axis. You can see that it bounces back. All right, so since the sum of the multiplicities of the zeros is, again, let's count, 1, 2, 3, 4, then g of x is a quartic function. All right, so I'm going to make that in black. So this is a fourth degree and it's quartic. Okay, so I've given you examples on how to identify those zeros and use that reasoning to justify your conclusion. So I would like you to try this last one and then submit that with your notes. Then we've got over here, let's go ahead and take a moment and define relative maximum. Okay, so another word for relative maximum, you might see local. So it's local or relative maximum. It's just a point where the graph changes from increasing to decreasing. So locating that point, I'm going from increasing to decreasing right here. So that is going to be a relative maximum. And so sometimes I'm going to ask you for the point, sometimes I'm going to ask you for the value. So it says to label and identify the relative maxims on the graphs of the function pictured to the right. So this one I am going to put here. The point is 1, 4. And the value is just going to be the y value. So that is just going to be a 4. So let's take a look at the second graph here. We're going from increasing to decreasing, and that's right there. But we also have one right here, increasing to decreasing. So we've got 2 points. I've notified them on the graph. So when I say label, it's sufficient to make sure those dots are on the graph. But let's go ahead and put the point. Let's say it's -2, 6. And then it looks like 2, 0. And so the value is going to be 6 and 0. Again, it's just going to be the y value. So let's take a look at the relative minimum. Now again, when you see relative, that's also local, depending on which text you might see that in. And it's just a point where the graph changes from decreasing to increasing. So where I'm decreasing to increasing. So if I look at that, it looks like on the graph, I've got this point right here, and that is 3, -3. So again, make sure you put that dot on the graph, and that minimum value is -3. So here again, we're going from decreasing to increasing. So there is a minimum there, and there's also a minimum here. So again, put those points on the graph, and then we've got -2, -4, and we've got 2, -4. And the value ends up being just -4 because they're the same value. We're just looking at the y value. All right, so now an absolute minimum is the absolutely lowest point on the graph. So we need to label and identify those points. So notice the word absolute. Notice that this has an arrow that goes on forever and in that negative direction. And then we've also got this one that goes on forever. So there actually is no absolute minimum on this particular example. Remember, it is the lowest point on the graph. So let's take a look over here. This guy right here is the lowest point on the graph. So this point is going to be 2, -3, and the absolute minimum value is -3. All right, so now let's take a look at some vocabulary here for absolute maximum. It's the absolutely the highest point on the graph. So I could definitely see that that point right there looks like -2, 6. So we'll have -2, 6. That maximum value is 6. But notice on this one, there is no highest y value because it goes on forever. So there is no absolute maximum. Okay, now let's take a look at the definition of the point of inflection. All right, so we talked a little bit already about where the graph changes concavity. This is also going to be one of the formulas that you'll need to utilize sometimes in order to find the point of inflection. So here is a key idea of when and how you can identify when a point of inflection occurs. So it can occur at one of three places. It can occur at a zero whose multiplicity is 3, which we've already kind of talked about. And we can also look at the inflection point where it's the approximate midpoint of a zero of multiplicity of 3 and the nearest relative max or min. Okay. And then we're going to look at examples on that. And then number 3, at the approximate midpoint of 2 consecutive relative max or mins. Okay, and sometimes it doesn't necessarily have to be relative, it can be absolute. But the idea you'll see in just a moment. So let's take a look at this first graph right here. It says, how many points of inflection does the graphed function below have? And then label their approximate locations on the graph. So if I were to take that, I'm going to try and show you that this obvious one is right here, which is that inflection point. And that just goes with condition number 1. All right, so I'm going to label these for you 1, 2, and 3. So that way you can kind of see which definition, which portion I'm referring to. So let me change this to, this is going to be like condition number 1 on there. And then it looks like on this particular spot, it says, let's see, let me go here. Let me color code this graph for us here. If you can see that there is a point between the multiplicity of 3. So you've got a 0 of multiplicity of 3 and the nearest max or min. So here is the multiplicity of 3 right here and the nearest max or min. Okay, so what we need to do, this idea right here, whoops, let me change the color, is from that point right here, what we need to do is find the midpoint. So let's take a look and find the midpoint between 0, 0 and the maximum, which is negative 3, 3. So the midpoint says that we are going to add the x's and divide by 2. Then we add the y's and divide by 2. So I am going to take 0 plus negative 3 and divide by 2. And then I'm going to take 0 plus 3 and divide by 2. So it looks like I've got negative 3 halves and then 3 halves. Okay, so if I were to take that point, negative 3 halves, negative 1.5, and then up 1.5. It's approximate. Okay, so on this point right here, you can see that the concavity changes, right? So now that's a point right here. And then now let's take a look at condition number 3. Well, we don't have condition number 3. It says the 2 consecutive relative max and mins. And so we don't have 2 consecutive max or mins. What we do have is another version of number 2, where we have the 0, and then we have um, a minimum. So now what we need to do is find the midpoint of these two. So let's take a look at the midpoint. Now some of these you can just obviously see by looking where the halfway point would be. But right now I'm just going to go ahead and show you those 2 points. So we've got 3, negative 3. And so what's going to end up happening is we're going to add up the x's and divide by 2, and then add up the y's and divide by 2. And we've got, put a black one on here, 1.5, and then down 1.5. Now it's approximate. Okay, we said the approximate midpoint. So that's what's going to happen here, is where it changes concavity at those specific spots. All right, so let me just kind of color code for you. This is concave down, this concave up, this is concave down, and this is concave up. Okay, we're going to get into more concavity in just a moment. So let's take a look at this one. All right, so this one, you notice that there doesn't appear to be a multiplicity of 3 on the x-axis. So we are dealing with not condition 1, not condition 2, but condition 3. It says at the approximate midpoint of 2 consecutive relative max or mins. So I look at this and I see max and min, so I need the midpoint of those. So let's take a look at that. So I've got 1, 4, and 3, 0. So the midpoint is going to be 1 plus 3, which is 4 over 2, and then 4 over 2 because 4 plus 0. So I get the 0.22. So the 0.22 is going to be that inflection point, and I want to kind of color code for you so you can start seeing that this is concave down. And this is concave up in purple. Okay. So this is the point of inflection. So we were supposed to label and identify the coordinates of all points of inflection for the graphs below. So we labeled it by having that dot, and then we found the actual coordinate of the point of inflection. So now, and just so that way you have it, that idea was based on 3 from above. Okay. So let's take a look at this one. We can definitely see that there is an inflection point right here, multiplicity of 3. We also need the halfway point between this point and this point. So we need to be able to find the midpoint of that. So we've got the point -2, 0, and then we've got the point 1, -5. Okay. And so we're going to go -2 plus 1 over 2. And then we're going to go 0 plus -5 over 2. And so we're going to get -1/2 and then -5 over 2. And so if we were to plot that point, it looks like that point, actually I need to clear that right here. So we were to identify the 2 inflection points. So there's an inflection point, and this is also an inflection point. So let's identify those. We have an inflection point at -2, 0, and at -1/2, -5 over 2. And let me just show you concave down, again, what it's going to look like. Okay, so concave down is any portion that looks like an upside down cup. So this looks like the upside down part of a coffee cup. And then concave up is going to be any part that looks like an upright coffee cup. So remember, you've got this point right here that goes up. So this is concave up. You also have this portion of the coffee cup. So in other words, if you were to take it, if it would hold water, then it's going to be concave up. If it is going to spill water, then it's going to be concave down. All right, so now let's take a look at the last page. So now we're talking about intervals of concavity, okay? First of all, they're open, which means you're always going to be using parentheses. You're definitely not going to be using brackets. And you're talking about the part of the x-axis where the graph is either concave up or concave down. So first, we would need to be able to identify those points. So we're going to identify the interval on which the graph functions to the right or concave up or concave down. So you might need to do a little bit of your midpoints, right? So in this midpoint, notice I don't have an inflection point on the x-axis, but I do have the midpoint of 1, 4 and 3, 0. So if I were to do that, I'm going to get the midpoint of 2, 2. So that right there is my inflection point. That's where it changes concavity. So again, if it's portion of a coffee cup kind of a thing, you should be able to see where it's concave up or concave down. So concave up on the interval from 2 to infinity, and it is concave down from -infinity to 2. Okay. All right, let's take a look here. We definitely have an inflection point here. And then if you were to take the halfway point, we would have to do our midpoint again. We're going to take -2, 0. And again, I'm focusing on the fact that there's a min or max. So that's 1, -5. So if I were to add those x's and divide by 2, I get -1/2. And then I also get -5/2. So I am looking up right about here as my inflection point. Okay, so now let me just color code these. I'm looking for concave down and then concave up. So I'm just going to color code these. So it is concave up on the interval from -∞ to -2. Again, always parentheses. And then it is also concave up on -1/2 to infinity. Again, it's always the x. So now I'm going to change to green. Concave down on the interval from -2 to -1/2. All right. And so come prepared with questions. You will need to complete this portion on your own and then turn in the notes once complete.